All right, so now let's talk about electric fields. And if you remember back in Unit 2 for AP Physics 1 or AP Physics C Mechanics, we talked about a gravitational field. And the gravitational field, just to help you remind, the gravitational field was the G. Remember we said force of gravity was equal to mg, right? And the G we sometimes call it the acceleration due to gravity or the gravitational field. And it wasn't a force itself, okay? It was a vector, but it was like related to calculating the force. And this G, if you remember, was given by this way. G, mass of the planet, divided by r squared, where r radius of the planet squared, or if you were like near a planet. But it was the portion of the gravitational force that was due to what was causing the gravity. So it's like if you had an object of mass, you multiplied it by the gravitational field, you would then get the force of gravity. So electric field kind of has the same thing. It has this relationship. Kind of like Fg is mg, the electrostatic force can be written by Q, charge times whatever we call this electric field. Now, similar to like this was caused by a planet or large object, large mass. The electric field is caused by the external charges that are going. They're created by the charges and the electric force created by those charges. So like if I have a little charge here and I want to know what is the force, the electric force that it's going to have, it's going to be due to all of these other charges that exist out here, a mix of charges. So let's say there are a bunch of charges. This would experience a net force due to all of these other charges. Okay, and that force per charge would be the electric field caused by these. These things would create an electric field that might act on this object. Similarly, like the Earth creates a gravitational field that if you put a mass there, it experiences a force. So electric fields are vectors, and they're very similar to the force, electric force. Electric field vectors, the direction is that a positive charge would experience a net force. So if you placed a positive charge there and the direction that the net force points is the same as the direction of the electric field. Now, gravitational field was always easy. It was towards the center of the planet or the mass. But if you had multiple planets, technically you could have a gravitational field that was the sum of different planets. And we typically, what's different in electricity is that we have multiple charges mixed together that interplay and create the electric field. Okay, so the electric field is related to the electrostatic force. Okay, so let's kind of like go through like some ideas. So first of all, electric field from a point charge. So let's say you had a point charge out here. It had a charge positive Q, and you placed another positive charge here. We'll call this Q2. Now this guy would experience a force. He would experience a repelling force, right? That electrostatic force, which would be K. And the two charges, Q times Q2 divided by the distance squared, right? If this was the distance from here to here, if that were distance R, that would be the electrostatic force that he feels. But we could say that this charge here, this Q, is creating an electric field, and you could say it's equal to Q2, this force is Q2 times the electric field caused by Q. This is a subscript, right? This is the electric field. This guy right here is the electric field. And that electric field, okay, times the charge that you placed here is the electrostatic force. You see the Q2s cancel. So the electric field from that point charge is KQ over R squared. It's like sort of just part of the law, the forces law. Just like gravitational field, which is part of the force of gravity, right? It's a part that just doesn't involve the charge that you're interested in. Okay. Now, electric fields are just like force vectors. They're vectors. You got to add them like vectors. You got to decompose them like vectors and things like that. Okay. So let's go through an example of how we would like do problems related to electric fields. So we have a proton is suspended as a positive charge. It has an elementary charge E. And we'll say mass of a proton, MP is the mass of a proton, is suspended in the air by an electric field at the surface of the Earth. What is the strength of the electric field? So it's suspended. So we're going to draw our free body diagram. He's going to have force of gravity. And then there's going to be, in order to prevent him from falling, like if it's just mass, it would just fall down. In order to prevent him falling, there must be an electrostatic force that's keeping it suspended. And then because the acceleration is 0, it's suspended there. We know the electrostatic force is going to equal mp times g. And the electrostatic force is just simply the Q times the electric field, which is, in this case, the charge on this guy is E, right? Times the electric field is going to be MP times G. And so the electric field would equal the mass of the proton times G divided by E numerically. And then if you looked up the mass of a proton multiplied by 9.8 divided by E, which is 1.6 times 10 to the negative 19, you would then get the electric field needed to suspend that thing, right? So that's kind of the idea. The force is related to, you take the charge of what you're interested, what's being subject to an external electric field, times its charge, that's going to give you the force. Let's say we have a proton enters a uniform electric field produced by two charge plates shown below. The magnitude of the electric field is this newtons per coulomb, and that makes sense what the units are, right? Because the force on the electric field is Q times the electric field. This is measured in newtons. This is measured in coulombs. So the electric field has to be measured in newtons per coulomb for those to cancel and give you newtons. The speed of the proton when it enters is 1.5 times 10 to the 7. What distance d is the proton be deflected downward when it leaves the plate? Ignore the effects of gravity. So this guy, because it has an electric field downward, it's pushing the thing downward, right? The direction of the electric field is the direction that a positive charge would experience a force. So the electric field's pointing down, so the charge is going to experience a downward force, right? Now, this is a little bit like a projectile motion because it's subject to an electrostatic force, which is equal to Q times the electric field, right? And that's equal to ma. So there's an acceleration that's going on. So let's think about our projectile motion setup, right? X, Y. We list out our kinematic variables. This is our process for projectile motion, right? So the horizontal displacement, right? So if we say right is positive and we make down positive because it's deflected downward. 12 centimeters, 0.12 meters. The initial velocity is 1.5 times 10 to the 7. The force is only pointing downward, so the horizontal acceleration is 0, and we just don't know the time here. But we could solve for the time here. Vertical displacement from there to there is positive d because it's pointing downward, right? The displacement vector looks like this, so the component in the vertical direction is downward. There's no vertical component initially at the start. It's only pointing to the right. Final velocity, don't know. The acceleration is downward. Here we go. It's going to be QE over the mass of the proton. It's going to give you the acceleration. That's QE over the mass of the proton. We'll plug in a number here. And I want to know this guy right here. This is what I'm looking for, and I need to know the time. But on this side, I have three pieces of information, so I can solve for the time. I'm going to use this equation because that's the one that gives me these three known quantities and one unknown. The acceleration is 0 in this case for this one, so it's just going to be 0.12 is 1.5 times 10 to the 7 times t, and you can solve for t. It's going to be 0.12 divided by 1.5 times 10 to the 7. So now we have enough information to solve for d. We can use the same kinematic equation here and get d is equal to 0t. It's 1/2 at squared. A is going to be this value right here, QE over the mass of the proton, right? And the time is 0.12 divided by 1.5 times 10 to the 7 squared. Now let's plug in these numbers here. The charge on a proton is 1.6 times 10 to the negative 19. The electric field they gave us was 4 times 10 to the 5th. And then you look up the mass of a proton, it's 1.6 times 10 to the negative 27 here. And then now we can now calculate, right, for all of these values using our calculator. Let me use my calculator real quick. And I get this is 0.00128 meters, which we'd call about 0.13 centimeters if you wanted something like that. Okay, so that calculation hopefully you can do, but like that's how you would look at using the electric field. Now, let's say you want to find the electric field from multiple point charges. This is a very common scenario you'd be asked to do, is to say, like, I give you a configuration of charges. I want you to tell me what the electric field is at a particular location. So there's a few ways to do this. This is the way I was taught, and I think it's kind of a useful way. It's just to reuse your forces process. You're going to place a positive test charge Q test at the location you're trying to find. You're going to draw a free body diagram at the test charge. You're going to calculate the F net. Not doing the MA part, just doing the F net portion of the F net equals MA stuff. And the net electric field will be the net force divided by that Q test charge. Because the Q test is kind of like this placeholder charge because you're going to divide it out, so it's going to go away when you put it into there. So let's kind of like see how that operates in. So given the charge configuration below, what is the electric field at point P here? Okay, so first we're going to put a charge here, Q test. It's positive charge. Well, it doesn't really matter, but just assume it's a positive charge. And it's like you're imagining you're placing it there. And then you're going to draw the free body diagram. Well, this positive charge will experience a force this way because it's repelling it. This positive charge will experience a force this way. We'll call it F3. We'll call this number 1, 2, 3, and then this is number 2. This one's a negative charge, so it's going to pull it towards it, right? Because this is a positive charge we put into place, so this would be F2. Okay, and so then we want to sum up these forces, knowing that we're going to have to decompose things in the x and y direction. Now this angle is 45 degrees because it's like a square here. This is D, this is D, this is 45 degrees. So this one would decompose our forces into F2 cosine 45 degrees, and then a downward one is F2 sine 45 degrees. Okay, now we're going to do F net in the x and the y direction. For the x direction, the F net is going to be, if we say it right is positive, it's going to be F2 cosine 45 degrees is pointing to the right, and F1 is pointing to the left, and that's it. And in the y direction, if we look at the net force, we're going to have F3 pointing up, so that's positive if we make up positive direction, and then F2 sine 45 degrees is pointing down. Okay, now what are these forces here? We'll just use Coulomb's law. So F2 is going to be these two charges. That's going to be K Q test times 2Q. Remember, don't put the negative sign in there because we've already factored that in based on the sign, based on the direction of our free body diagram, divided by the distance here. Well, this distance is D, this is D. This is the hypotenuse of that square. That's D root 2, just using Pythagorean theorem. So it's going to be D root 2 squared. And then F1 is going to be the force from here to here. That's going to be K Q test times Q, and the distance there is D squared. And then, oh, this one, with the cosine 45 degrees, we need to put a root 2 over 2 if you want, or you can just use the decimal. We forgot the cosine of 45 degrees. So that's the x. So this is going to be, let's see, this, when you square it, that'll be 2. That will cancel. Well, that will cancel with that one. You have square root of 2 over 2. So you have square root of 2 over 2, K Q test Q over D squared, right? And then this is minus K Q test Q over D squared. And you can factor out K Q test Q over D squared, and you'll get root 2 over 2 minus 1 here. And that's going to be a negative number, I think, so it's going to be technically pointing to the left. But that would be F net in the x direction. Now, the electric field in the x direction, then, is you just divide the Q test out, right? Because that's how we relate the electric field. The Q test times whatever electric field is in is going to be that electrostatic force. So you just divide that out, and that gives you the electric field in the x direction. Okay, root 2 over 2 minus 1. Now, let's look at the F net in the y direction here. You're going to have F3. So F3 is going to be K Q test times the same Q test Q over the distance squared. And then this one, F2, is going to be K Q test times 2Q, because it's double the charge, between here and here. Oh, yeah, this is the F2, right? We already calculated F2 over here, over D root 2 squared. Sine 45 degrees is also root 2 over 2. So that 2's cancel. So you're going to get pretty much the same thing as we did before, right? It's just it's going to be 1 minus root 2 over 2. So it's going to be KQ over D squared Q test 1 minus root 2 over 2. And again, if you want to find, that's the net force in the y direction. So the electric field in the y direction, you just divide out that Q test. Okay, so you just do that, minus root 2 over 2. And so this would be the y component of the electric field, and this would be the x component of the electric field. Okay, so the Q test is nice because it just allows you to just think of it as like a forces and a free body diagram. It's just like the most natural way. You can do it without the Q test. You just realize you're just going to drop. It's like you're going to do net force, but you're just going to drop one of the Q's because you're only looking at the charges that are external to this charge, right? That's these things create the electric field acting on this guy. right? Let's do another example here. Find the electric field at point P right here, right? We have two charges here. And again, put a positive Q test here. And that way you can just do this. You say like, oh, this is a positive charge. It would cause a force this way, F1. And because of the same charge, same distance, it's going to be the same F. So I'm just going to call it F. And then this charge is going to cause a force this way. And that F is going to be that electrostatic force. It's going to be Q test over the distance squared over A squared. Now, we still got to add them like vectors, right? So one thing you'll notice because of the symmetry here, this angle, by the way, is because this is a equilateral triangle. We know that this whole thing is 60 degrees, but this component right here is only going to be 30 degrees. It's going to be half of it. So we're going to decompose it. We have an F downward here. So this would be F sine 30 degrees. And this guy right here is going to be F cosine 30 degrees. And let's decompose the other force on the left here. It's kind of down and to the left, F sine 30 degrees. And this one here is going to be F cosine 30 degrees. Notice that these two are going to cancel each other out because one's pointing right, one's pointing to the left. So in the x direction, the F net is going to be 0. The y direction, the F net is just going to be, if we make down positive, it's just going to be both of these vectors added up. It's going to be F cosine 30 degrees plus F cosine 30 degrees, which is just 2F cosine 30 degrees. And that's going to be 2KQ test over A squared, right? Times cosine 30 degrees, which is root 3 over 2. And that gives you the net force in the y direction. And there's no net force in the x direction. So that means the electric field in the x direction is 0. So the electric field in the y direction, you just divide out the Q test to this side, and you get KQ over A squared root 3. And that would be the net electric field. So that's kind of like when you have multiple point charges, that's a way you can calculate the electric field like that, okay? Thanks for checking out this video. I hope you found it really helpful. If you'd like more support, maybe you need more multiple choice practice, maybe you just need more guidance and things like that, I have plenty of information on my website. If you look in the description below and go to www.bothellstemcoach.com, I will explain all the ways I help students be successful in their AP classes.